So we've talked about measuring positions and how, for example, in the sky, the moon's about half a degree across. Vertical to horizontal is going to be 90 degrees. So this actually gives rise to a way of telling where something is in the sky by your direction you're facing and by the how high up you look. And this is what we call the horizon coordinates. The horizon coordinates are sometimes called altitude and azimuth. Altitude is how high above the horizon. So that's how high above the horizon. And azimuth is how far around from north it is. So for example, 0 degrees azimuth means due north. 45 degrees azimuth means going from north over this way, and so that's going to be northeast. 90 degrees azimuth means east. 180 degrees azimuth means south. 270 degrees azimuth means west. So basically, if you look at a compass, it has numbers, 0 to 360 or 1 to 360 around a compass. That number is the azimuth. Okay. In that case, magnetic azimuth, but it's the azimuth. So it's the compass heading. Okay. Altitude is how high up. So if I told you, hey, go out tonight and look at this really cool thing, it's going to be at an altitude of 60 degrees, and it's going to be at an azimuth of 120 degrees. So you go out and you look, and 90 degrees is going to be exactly due east. Okay, so 30 degrees more, so 30 degrees south of east, that's going to be 120 degrees azimuth. 60 degrees means you go up here 2/3 of the way up to straight up. Straight up is like that, so you want to go 2/3 of the way up. That would be 60 degrees azimuth. So you face, that'd be 60 degrees altitude. So you'd face the azimuth of 120 degrees. You would look up 60 degrees. That's altitude and azimuth, okay, or azimuth and altitude. And so that's how you do it. Now, one of the labs that you're going to be doing later in the semester is going to be learning to identify stars. So what you'll do is you'll be using your planisphere. You'll be identifying stars in the sky, and then what you want to do is estimate the azimuth and the altitude. Okay, and so there's different ways of doing that, and so I'll record a video that shows you a way of doing those kind of estimates to figure it out. Okay, but these are the horizon coordinates. Now, there's a problem with horizon coordinates. Okay. The problem with horizon coordinates is that, well, Earth is round. So you got Earth. If you're standing in one part of the Earth, that's straight up. If you're standing on a different part of the Earth, something else is straight up, which means you have a star up here. On this part of the Earth, you look that way to see it. On this part of the Earth, you look that way to see it. So there might be a star out there that's east of somebody, but west of somebody else, and north of yet somebody else. So that means the altitude and azimuth depends on where you are. So the altitude and azimuth of stars in Dallas and Fort Worth is going to be different than the altitude and azimuth of stars in Houston. It's going to be different than the altitude and azimuth of stars in New York City. Now, it's less different between Dallas, Fort Worth, and Houston than it is between DFW and like Chicago or someplace further north. So there's less of a difference, but there is a difference. So different places are different. The other thing is Earth turns. So as Earth rotates, stars rise in the east and set in the west, And so that means that the altitude and azimuth change as you go. So the altitude and azimuth depends on where you are and when you are. Now that actually turns out to be really interesting. It's complicated for astronomy students because you know where you are. And you know what time it is, you want to go out and look. So you got to calculate where are these things in the sky. The star wheel here is not very accurate, but gets a rough idea of altitude and azimuth here. Your planisphere, you can adjust it to know what direction to face and roughly how high up to look to see something. So this is like an analog computer for figuring that out. Okay, now the interesting thing is, in the ancient world, they had something called an astrolabe, which was a tool that was kind of similar to that, in which they used to figure out, you know, where these things were in the sky. Okay, that's why you got to get the one that's between the 30 and 40 degrees. That's going to be the sky for us here in the DFW area. Okay, if you live someplace else, you would get one that's a different range in there. Okay, so now, get horizon coordinates with altitude and azimuth. Fantastic. But it depends on where you are and when you are, which is a really interesting thing. Because, again, back to Earth, back to the fact that it's round, and where you are makes a difference what the sky looks like. This idea of horizon coordinates is vital to celestial navigation. You know, long before they had GPS satellites, you know, you got a ship out on the sea, where is it? You know, even when they first started doing transoceanic air travel, you had to have a navigator on board. In fact, a lot of the really old aircraft had a window in the roof of the aircraft in the cockpit for the navigator to take sightings on things out the roof so they could see where the stars were. Now, that's because, remember I said, it depends on where you are and when you are. If you know when you are, and you know where a star is in the sky, you can figure out where you are on Earth that makes the star in that direction and that altitude. So you can work backwards. You know, the altitude and azimuth are determined by where and when. Well, this is like algebra. You know, if you know three things, okay, if there's three variables and you know two of them, you can solve for the third one. Okay, so that means if you can figure out the altitude and azimuth, you take a sextant, a device that measures the altitude and the azimuth, and then that tells you that if you know what time it is accurately, you can then figure out where you are. That's how navigators work. In fact, even today, the Air Force, the B-52, it's a very old aircraft. They still have windows in the ceiling so they can actually take sightings off of, even though we now have GPS. For a number of years, the military quit teaching celestial navigation because they said, oh, well, we got GPS. And then they realized that GPS signals can be actually jammed, or during a major geomagnetic storm, you can lose GPS. And then your ship or your soldiers don't know where they are. Okay, and so to fix that, over the last several years, they've been teaching celestial navigation again. And so what they're going back to teaching rough celestial navigation. I actually once was asked by a boat club to teach rough celestial navigation, and so I gave a couple lectures here about how you navigate by the stars. And then what we did, we actually packed up a telescope and sailed out to an island and set it up, and we did some night observations that way. But that's you know, you can do celestial navigation, so that's doing this horizon coordinates backwards. Now, in horizon coordinates, a couple other terms that you want to know. One of those terms is the meridian. The meridian is an imaginary line that runs from due north to due south, going straight overhead. Why is that important? Well, things rise in the east and they set in the west. So that means midway in the sky is on the meridian. That's when things are highest in the sky. And so for an astronomer, you would want to calculate when are things highest, because that's the best viewing. When's it on the meridian? Okay, so that's this midway point, highest in the sky. We'll get back to that later. And the point straight overhead, directly over your head, that point is called the zenith. And so that's the point directly overhead. So on your star wheel, the zenith is located right about there somewhere. Okay, so this is the basic idea of horizon coordinates. The big advantage is you can tie it to your location, so if you measure the horizon coordinates, altitude and azimuth, you can calculate your latitude and longitude. Okay. If you know your latitude and longitude and what time it is, you can figure out the altitude and azimuth. You know, conversely, if you know your latitude and longitude and you measure the altitude and azimuth, you can figure out what time it is. Okay. So all these things, you know, I mean, it's algebra. You got 3 variables. If you know 2 of them, you can solve for the 3rd one. Okay. Now, the problem is all the coordinates change. Over time, as the stars rise and set, the altitude and the azimuth change. It depends what time it is. It'd be really nice if we had a coordinate system that did not change. And it turns out we do. It's called the celestial coordinates, or right ascension and declination. So that'll be our next topic, is those kind of coordinates.